Alright, welcome back everybody. In this video we are going to talk about the nth-Term test for divergence. This is section 10.3 of AP Calculus BC. So in Unit 10, for about the first half of the unit, our entire focus is going to be on looking at tests that we can use to determine if various infinite series converge or diverge. For instance, in the last lesson we learned that geometric series converge if the absolute value of r is less than 1, and diverge if the absolute value of r is greater than 1. That test works really nicely for when we have a geometric series. In the first lesson of the unit, we looked at how we can use partial sums to determine if any series converges or diverges, but using partial sums is very cumbersome. I could use that technique for every single series, but it gets to be just such a mess for us to try and analyze whether the limit of these sums approaches a value or not. So over the next several lessons, we're going to determine a battery, an arsenal of tests that we can use. The test that we're going to learn today, the nth-term test, is completely different from all the other ones. Because all the other tests we're going to have, you're going to be able to use them and you'll be able to make a statement like this series converges because of passing this test, or the series diverges because of failing this test. But with the nth-term test, this is the only test that we're going to learn that we can't use to show convergence. Okay? We can only use it to show that an infinite series diverges. We're going to get to that, though, a little bit further along. All right. Last lesson, when we talked about geometric series, we saw that they converged if the absolute value of r was less than 1, and they diverged if the absolute value of r was greater than or equal to 1. One of the reasons that this happens is because when absolute value of r is greater than or equal to 1, that means that these series, the terms of this series, are not getting closer to 0 as n gets larger. Okay? This leads us to our first observation about the convergence of series. If a series converges, that means that the limit as n goes to infinity of a sub n has to be equal to 0. Think about how that happens. When we're saying something converges, that means that it's going to approach a finite value when we take the limit of the sum of all these infinite number of terms. Well, if the last term is approaching anything other than 0, it's going to add substantial value to the sum, which means that it's going to keep the series from converging. And so in order for a series to converge, the nth term has to get closer and closer to 0. However, it says here, it's crucial for us to note that the converse of this statement is not true. Okay, knowing that the limit as n goes to infinity of the series approaches 0 doesn't tell us whether the series converges or diverges. Okay, this is going to be the inconclusive situation when we talk about the nth-term test for divergence. And let's show you this in action with a particular series. All right, let's look at example 1. We're going to investigate the partial sums of this series to reinforce that the converse of our original statement is not true. And we have looked at the partial sums of this before. The first partial sum is just 1. And then the second partial sum is 1 plus 1/2, which is 3/2. And then the next partial sum is 1 plus 1/2 plus 1/3, which is going to be, what is it, 11/6? 11/6. And the fourth partial sum is going to be 1 plus 1/2 plus 1/3 plus 1/4 plus plus 1/4. Sorry, I got into. And you notice that these terms just keep growing. And a couple of lessons ago we talked about how to find partial sums on our calculator. Let's take a look at what happens when we take the summation of this for a bigger partial sum. So let's take the partial sum from 1 to 50. And it's 4.4, etc., etc. And if I take the partial sum with the first 100 terms, keeps growing. And if I take it with the first 150 terms, it keeps growing. And if I continue to put larger and larger and larger n values in here, or larger and larger upper values in our summation, this is just going to continue to keep growing, even though the terms do get closer to zero. This series, the harmonic series we've mentioned before. We're going to talk about it more later on in the course in this unit. But it's kind of like the dividing line, where it's the series that grows just fast enough that it doesn't converge, where series that are smaller than it tend to converge, and series that are larger than it tend to diverge. But again, we'll get into that more later on. So you notice that the converse of our statement up here is not true. If the limit as n goes to infinity of a sub n equals 0, that does not mean that the series converges. And that's what makes this nth term test different from all the rest. This is the contrapositive of our original statement, and that's the nth term test for divergence. If the limit as n goes to infinity of a sub n doesn't equal 0, then we can definitively say that the series diverges. So the way the nth term test works, we find the limit as n goes to infinity of a sub n. If it's not equal to 0, it diverges. If it is equal to 0, it is inconclusive. And you see my big starred note here. It's important to realize we can never conclude from this test that a series converges. The only two conclusions that we can draw: it diverges if n doesn't equal 0, but if n does equal 0, then the test is inconclusive. All right. So in example 2, we're going to determine if these series diverge using the nth term test. We can't determine if they converge. We can only determine if they diverge. So all we're going to do in order to do that is we're going to take the limit of the nth term of the summation. So the limit as n goes to infinity of n over n plus 1. This limit is going to be 1. That doesn't equal 0. Therefore, this series diverges. All right, limit as n goes to infinity of n squared minus 1 over 2 to the n. Now I know that 2 to the n grows a lot faster than n squared, so that tells me that this limit is going to be 0. If you're not so good at figuring that out, you might have to apply L'Hopital's rule here. You get an infinity over infinity, but hopefully you've gotten to the point in your life, calculus-wise, where you understand the difference in relative growth rates of most of our common functions, and you can just look at a fraction like this and understand that the denominator is going to grow significantly faster than the numerator, which means that this limit is going to approach 0. Since the limit is 0, that doesn't mean that we can conclude that it diverges. That means that the nth term test is inconclusive. And if we want to decide if this series converges or diverges, we're going to need another test. And don't worry, till we're done, we will have plenty of tests that we can use to determine whether this particular series converges or diverges. All right, part C. Limit as n goes to infinity of 2 to the n over 3 to the n plus 1. All right. If I take this limit, and again, if you're stuck, we're in a learning mode here. If you're stuck and you're not sure about what this limit is, it's going to be infinity over infinity. We can use L'Hopital's rule. We could try to investigate what's going on with the help of our technology. 3 to the x plus 1, and I could set up my table to ask me values here, and go to my table and put bigger and bigger values in for x. It's really not going to take too many of them. I can see that this is a phenomenally small number, so this does indeed approach 0, telling us that the nth term test is inconclusive. All right, next one. Limit as n goes to infinity of n times the sine of 1 over n. That one's not so pretty for us, but I'm going to do a little bit of algebraic manipulation that's going to help us here. This is the limit as n goes to infinity of sine of 1 over n all over 1 over n. And at this point in time, I'm going to let m be equal to 1 over n in order to modify this limit, and it's going to turn into something that you're going to like. As n goes to infinity, since m is 1 over n, that means this is going to be the limit as m goes to 0 of sine of m over m. This is a limit that you should recognize. The value of this limit is 1. 1 is not 0, therefore, by the nth term test, we can say that this series diverges. All right, part E. Limit as n goes to infinity of n plus 3 factorial over 3 factorial, n factorial, 3 to the n. We got to figure out what this is. All right, we can simplify this a little bit. It turns into the limit as n goes to infinity of n plus 1 times n plus 2 times n plus 3. So we've got a cubic polynomial in the numerator. Basically, I just canceled out the n plus 3 factorial and the n factorial. Now I've got a polynomial over this exponential down here. The exponential is going to outgrow the polynomial, so this limit is going to be 0. Therefore, the nth term test is going to be inconclusive. Take the limit of this one. Do you folks remember seeing this limit before? This is a very famous limit, the limit as n goes to infinity of the quantity 1 plus 1 over n to the n. If you find that limit, we've found it before. That's the definition of E. This is the limit as n goes to infinity of 1 plus 1 over n to the n is equal to E. That's how we define the value of the constant E. E does not equal 0, therefore this series diverges. Next one. This is the limit as n goes to infinity of n factorial over e to the negative n. This is equal to the limit as n goes to infinity of n factorial over e to the n. Now exponentials grow a whole lot faster than pretty much every other function. The one function that's really common that they don't grow faster than is factorials. And we can, illustrate this a little bit more, and if you want to, you could talk to me. I'm a little bit short on time here, so I don't have a good opportunity to, show you this in practice in this particular video because I want to finish this lesson out. But factorials grow faster than exponentials, which tells us that this limit is going to be infinite. Infinity doesn't equal 0. I feel kind of silly making that statement, which tells us that this series diverges. And one more. Limit as n goes to infinity of 3 to the n over n cubed times 2 to the n. This one also goes to infinity. And you can test yourself in finding and showing that that limit goes to infinity, but we've found limits going to infinity before, so you're totally capable of doing that. And since that goes to infinity, infinity doesn't equal 0, that tells us that this series diverges. All right, so that's what the nth term test is and how it works. Okay, we'll see you next time. We'll come back with video for section 10.4 when we're going to talk about the integral test for convergence. All right, do some practice with the nth term test. Get this under your belt. This is going to be a test that we're going, we're just building this tool shed. Now we're up to 3. We've got 3 ways that we can talk about divergence and convergence of series. All right, everybody have a great rest of your day. See you next time. Bye-bye now.